Okay. Now, just as a reminder, we do have a quiz on Monday. Now, Monday's quiz will be concerning the stat key. All right, maybe a couple of questions from the book, but the book we're not going to be reading much from the book this week. So we're going to be using stat key to for the source of the questions. So pay attention, and the quiz should be easy. Should be very easy if you know exactly how to interpret a stat key result. All right, so that's what we'll do. And so the first thing we're going to do is actually go to the book. Now, in chapter 20, it's talking about confidence intervals, and what we're estimating in chapter 20 are proportions. And in chapter 21, we're going to be using confidence intervals to estimate population means. But we're not going to be reading very much of the chapters. Now, if we were going to be using formulas to create what are called confidence intervals, then we would read the entire chapter, both 20 and 21. But we're not doing that. The math department actually does not want us to do that, because this course is not a traditional statistics course. So what we're going to do is use the StatKey software to create or to simulate a confidence interval. We'll say simulate. But I have to define what a confidence interval is first. And so anyway, when we get a sample, then maybe get a sample of 100 people, and we're going to be asking them a question or measuring something. And we get a result for each of the 100 people. We're either going to be calculating a mean, or we're just counting and coming up with a proportion. Okay, the number of people divided by the total people that are surveyed. So one of those two things we're going to calculate, either a mean or average, or a proportion, a sample proportion. Now, if each of you in the class decided from a population, let's say the population has 1 million people in it, if each of you sampled 100 people, and you would get different results, because you would probably have a different group of 100 people, each of you. So it would be very unlikely that 2 or 3 of you would match and pick exactly the same sample. So the results would be different. The sample results would be different. And the question is that a good way of estimating the population? All right. So if we're, for example, if we're interested in the proportion of people who are interested in voting for a candidate A versus a candidate B, then we're just going to, ask people which one do you prefer, and we'll just count the number of people, let's say, who like candidate A versus candidate B. And once we have that count, we divide it by the number of people we asked the question to, and that's our proportion. All right. So again, your answer will probably be different than your neighbor's answer. It would be all different. Everybody would have a different sample proportion. So that is called, by the way, a point estimate. Makes sense. One number or point on the number line is representing an estimate of the population value or parameter. Now, the population proportion would not be known unless every person in the population voted and we came up with a result. So the question is a point estimate a good estimate or a population value? Well, since everybody's point estimate is going to be different, it's probably not a good estimate, that just by itself. So what we want, which is a better idea, is have an interval of values, any of which could be the population value. So what we're hoping is to create an interval of values, let's say from 3 to 5 or 4 to 6, whatever the interval is, and say somewhere in between those values is the true population value, somewhere inside that interval. And that's what we call a confidence interval. Now, the word confidence has to be explained, okay? And in the video last time on what they call bootstrap confidence intervals, it was explained to you. Maybe it didn't make much sense, but what I'm going to do today is go over that, what we mean by confidence, or another way of saying it, level of confidence, and how that affects the interval that we come up with. So the definition is right here, confidence interval. It says it's defined as an interval of values computed from sample data. So the sample that you get, you compute this so-called interval. And it says that is almost sure. It's never going to be 100% sure, but almost sure to cover the population value. Now, the typical confidence level, we call it confidence level, is 95%. And that's what I'm going to explain now going into StatKey. So what we're going to do is leave the book and let me go into StatKey. Let me just make sure I highlight StatKey here. Okay. And we'll share the screen with StatKey. Now, hopefully some of you, I would be surprised if all of you, but some of you have gone into StatKey and took a look. Again, to get there, just type in StatKey into your browser, and the very first one that pops up probably will be the one that you want, because it mentions the name Locke. And remember, this was developed by a family of statisticians, and her name is Locke. All right, so this is StatKey. And what we're going to do, where we going to see the description or definition of level of confidence, the best way of seeing it is to go into this section of the screen here that says sampling distribution. So we're going to pick the proportions, since we're talking about proportions first. Okay. So this is our screen. And what we're going to do is pick, we're going to pick a one of these data sets. All right, these data sets in this particular screen represents a population of values. Actually, this is a proportion, so let's not do that. Let's do something different. With proportions, we can create our own data set by hitting this Edit Data button here. So for sampling distributions for a portion, I'm going to hit that there. And actually, doesn't allow me to do that. Oops, all right. Maybe Edit Proportion does. There we go, Edit Proportion. All right, so I'm going to pick a proportion for a population, and somebody give me a proportion between 0 and 1. Any decimal between 0 and 1. Make it not too small, not too big.
0.24.
0.24. Okay, so we'll type in 0.24. Yeah, you said 0.24. That's it, right? Okay. So we're going to pick 0.24 as our proportion. All right, that's our population proportion. Now the sample size, we're going to make, well, it says 200 here. We can leave it as 200. That's fine. Now, what we want when we do a sampling distribution for a proportion is we want to make sure that the sample size times or multiplied by the proportion is bigger than, or at least as big as 5, and 200 times 1 minus the proportion is also bigger than 5. So in this case, you pick 2.24, and that comes out, if you multiply that by 200, you get 48. And 1 minus 0.24 is 0.76. And we get 152, I believe, for that. So both of those numbers are much bigger than 5, and that's good. So that's what we want to make sure is those two multiplications I just did are true, bigger than 5. Now, what we're going to do is we're going to just pick a sample from this population. All right, the sample is so let's pick one sample. And the sample size again is 200, right? So in this particular case, the computer, this is just a random number generator, it just picks numbers. It picks 47 out of 200, which is 0.235 as a proportion. If you divide those two numbers, that's our sample proportion. I pick another sample, it's time to pick 43 out of 200. So it's just randomly picking numbers, counts. And suppose I pick another 10. Notice they show up here, okay? And if you run your cursor along here, you see that particular sample over here, and the count and the sample size. So I'm going to pick another 1,000 of these. All right. So there's now 1,012 of these samples, okay? Each with a sample size of 200. Let's say 200 people. Each one of those has 200 people. And each one has a different count of the number of people that are answering a certain question a certain way. Let's just, you know, say anything about that, whatever that question is. And you're hypothesizing that 24% of the population, because you said it came up with 0.24, 25%, 24% of the population are going to say yes to one of the questions. Okay. All right. So here's a distribution of the samples that are selected from that population, samples of size 200. All right. And let's take a look at, and each one, and by the way, each one of these samples, we can create an interval around it, a confidence interval. I'll show you in the book how they do it. You're not going to be responsible for calculating it the way the book does. We're going to use StatKey, but I'll show you how it's done in the book. So on the screen here, there's on the right side here, it has a little button here called confidence intervals, which I'm going to press. And I think this was shown last time in the video, but each of the green lines represents an interval for one of these, for one of them. And actually you can see it show up here. You can see if I pick this one here, notice it shows up on, I don't know if you can see it, but it shows up on the right side there in the green. If I pick maybe one of these over here, it's going to show up with the red. Now, what do the red represent? The red represents intervals. Now, intervals are just a line segment, which has a low end and a high end. Each of the red ones, the interval runs from somewhere over here to somewhere over here and does not cross the line in the middle. Now, the line in the middle is what? 0.24. That's the number that somebody gave me in class, 0.24. That's the population proportion. Unknown, by the way, but we're choosing it just to illustrate this thing. Now, there are the green lines here represent intervals that have this line here, have this point here, 0.24, inside the interval. Can you picture that? So there might be a green line here that runs from here to here. And inside that interval is this 0.24, okay? The red lines represent intervals that do not have 0.24 inside them. Right? Make sense? So, in this particular case, out of the 1,012, and it shows it right here under the word coverage, out of the 1,012 samples that were chosen, 959 of them are green. 959 contain the population parameter 0.24, and the other ones, which is what, 40, that's 53 of them, the difference between 1,012 and 959, 53 of them do not. 53 of them are these red lines. So what it's saying here basically is out of the 1,012 intervals that we chose, 959 of them contain the true population parameter, 0.24, and the others, the 53 of them, do not. So what is the percentage that do contain the population parameter? It says 94.763%. We could say, we can round that up to 95%. So almost 95% of these intervals actually contain the population parameter. So when we say something like, I want a 95% confidence interval, I want to create a 95% confidence interval, what I'm basically saying is, I am betting when I create the interval that that interval will be one of the green ones and not one of the red ones. All right. In other words, it's one of these 959 green ones, and it's not one of the 53 red ones. If the true population parameters inside the interval, then we say we are successful. We have captured inside that interval the true population parameter 0.24. All right, we've captured it. If we're one of these red ones, we did, but we don't know that ahead of time. This is the point. We don't know. So we say with 95% confidence, that's why we say confident. We're confident, 95% confident, that the interval that we have does contain the population parameter 0.24. All right? Whatever one that we end up choosing, because we don't know whether it's a green one, we don't know if it's a red one. All right, we just don't know that up front because this 0.24 was unknown. All right, we're just assuming 0.24 here, but it's typically unknown. We don't know what it is. So here's the deal with interpretation. When you create, and we'll do so with StatKey, we're not doing it here, but we'll do it in another screen. When we create a confidence interval, when we say it's 95% confidence interval, what we're saying is the following. We're saying we're 95% confident that the interval that we created contains the population parameter, okay? We do not mean, and you should write this down, and we'll I'll give you an example that I'll post over the weekend. It does not mean that the probability that that particular interval contains the population proportion is not 0.95. It does not mean that. All right, because either once you choose that interval, it's either that it contains the true population parameter or it doesn't. We can't say there's a 95% chance that it does. Right? It doesn't mean that. Okay, it doesn't mean that. What it means is that if we did this process of creating samples, if we repeated this samples 1,012 times, all right, 95% of those samples will contain it, and we're hoping that the sample we chose is one of those samples. That's what we mean by 95% confident. Right? So it's not a probability in the classic sense of probability. Right? So if you see on a test something like, please interpret the confidence interval, and it says, well, there's a 95% chance that the population parameters within these two values. And you know that statement is false. It's false. It doesn't mean that there's a 95% chance between those two values. And that's because it's just one sample we're looking at. We're just looking at one sample. Okay? Does that make sense? I hope it makes sense to you, because with one sample, we just don't know. We can't say 95% probability. We just can't. But we could say 95% confident because it could. There's 95% of all the samples that we that we're choosing from the sampling distribution. 95% of them do contain the population parameter, and so in that sense, we're 95% confident that we chose one of those and not one of the ones that do not contain it, the 5% that don't. So it's a little subtle thing there that in terms of interpretation, and that's what's tested on the final exam. That's what's tested on test number 3, right? Just that simple difference between those two ideas. And you just need to avoid the idea of probability when you're dealing with confidence intervals. It's not a probability, 95% confidence. Right? It's not a probability. All right. Now, how do we find a confidence interval? We're not going to use this screen here. The only reason I picked this screen is to illustrate this idea of what level of confidence means. All right. 95% in this case here, right? 95%. All right. So what screen do we pick? Now, to get back to the home screen, we can always click the Stack Key button here. That takes us back to the home screen. It always does. All right. If you're interested in knowing how to get back, that's all you do is click that Stack Key button. What we're going to do is pick this middle column up here where it says Bootstrap confidence intervals. That's where we're going to create our confidence intervals. There will be 4 types of confidence intervals that we will choose: for single mean, single proportion, difference in means, difference in proportions. Now, these last 2, difference in means and difference in proportions, we will deal with that on Monday, next Monday. All right, next Monday, we will deal with that, these 2. What we're going to deal with today are the first 2, single mean or single proportion. Forget about the median and standard deviation. We're not going to create confidence intervals for those, although Stack Key created this software where it could do that, but we're not going to do that. We're simply going to use the mean or the proportion. So chapter 20 in your book deals with confidence intervals for proportion. So let's go back to the book for a minute. And let's hold on one second. Now, if you look at your syllabus, where it has information about what we're covering, in chapter 20, it just mentions 2 sections, 20.1 and 20.2. All right, 20.1 and 20.2. And the only things that I want you to learn from 20.1 and 20.2 is 20.1 is, of course, the definition of what a confidence interval is. And then it talks about levels of confidence. And I just described to you using Stack Key what a level of confidence means, what it literally means. Okay. And by the way, this book does a very poor job, I have to tell you, of describing the level of confidence. That's why I had to show it to you with the Stack Key software. It's kind of ironic that we have to use their software to correct for their error in the book, because they're saying you're willing to take a 5% risk that the interval does not actually cover the true value. That's incorrect. That contradicts what I was saying earlier. All right. It's not really a risk in that sense. All right. It's very misleading to say it in this way. What they really mean is that that the interval that you come up with could be one of the 5% that do not contain the true value. It's not really a risk or probability. All right. And it makes it sound like it is in this statement here. So I don't like the way they described it here. And that's why whatever you read here, don't worry about it so much. I'm not going to test you on this here at all, except for the idea in general what a confidence interval is. But I think you'll know what it is shortly when we do a couple of examples. All right, so let's go to the next section here. Now they give some examples of confidence intervals here using proportions. Now, I want you to pay attention to this formula in the middle here. It says a confidence interval can be also defined for a proportion as and I would replace percentage, I would replace it with proportion. I'd say a sample proportion plus or minus a margin of error. Okay? A sample proportion plus a margin of error. Let me see if this is a good example. Here, take a quick look. Yeah, this is fine. We'll use this here. We'll just use this one example, example 20.1. It says in a poll reported in Sacramento Bee, 54% of respondents said that they think California should legalize marijuana beyond its use for medical purposes. Obviously, this is old, right? 2013. All right, old. 54%. All right. In an accompanying graphic, the following information was provided. All right. 800. This is a sample size, right? 834 registered voters were sampled. Right. That's number one. And number two, they said the results carried a margin of error of plus or minus 3.5. Now, when they say 3.5 percentage points. So when you create a confidence interval for proportions, I would always use decimals. Don't use percentages. I know they say it in the book, it's okay, but I don't recommend it because when you do arithmetic, it's better to use decimals, right? So 0.5, 54% is 0.54. I would use 0.54 here instead of 54%. For the margin of error, 3.5 percentage points, I would convert that to a decimal by dividing by 100. That's 0.035. So 0.54, and then what you're going to do is take your sample proportion, which is this 0.54, and you're going to add and subtract from it the margin of error. So when you subtract 0.035 from 0.54, you get 0.505. Now they express it as a percentage. And then when you add 0.035, the margin of error, to 0.54, you get 0.575. And what these are the endpoints of an interval. And endpoints of an interval. And if it is a 95% confidence interval, the way to interpret this is to say something like, I am 95% confident that the true population mean is somewhere in between these two values. Okay. Now, if you have picked another, if another newspaper, let's say let's the Philadelphia Inquirer, all right? Let's say they did a poll about California for some reason, I don't know. And they came up with 52% of respondents, and they said the margin of error was 3%. You would come up with a different confidence interval, right? Your sample proportion will be different, and your margin of error is going to be different. And when you add and subtract them, you'll get different endpoints. Okay, so some of you will get one result, some of you will get another result. Okay, even if the margin of error is the same, the sample proportions are going to be different for each sample that we would come up with, different answers. So in each and every case, whatever confidence interval we come up with, we will not say that the probability that the true population proportion is between those two values is 95%. We will not say that. That's not the probability. It's not a probability. We would say we're 95% confident that this particular interval contains it. All right, as opposed to some other interval that somebody else might have come up with. In other words, we're hoping that this interval is one of those green ones and not one of those red ones, like we saw before. Okay, so that's the way I want you to interpret it. It's the correct way of interpretation, by the way. All right, and that's why you have to listen to my lectures on it, my talks on this, so that you do know the proper interpretation. Now, in this particular case, notice that they value 50% or 0.50 is not contained inside here. All right, in this interval. This interval is actually completely outside of this 50%. So we could say with a high degree of confidence that the majority of California voters believe marijuana should be legalized. Okay, the majority means greater than 50%, right? 50% is not inside this interval, and therefore we could make a statement like that. That would be okay. We would say with high confidence, with 95% confidence, we could say majority of California voters believe marijuana should be legalized. Because why? Because this entire interval is greater than 50%. Now, it is possible that you do another sample, all right, of size 834, and you come up with a confidence interval where the left endpoint is lower than 0.5 or lower than 50%, then you can't make a statement like that, all right? Because it is possible that that less than a majority, all right, believe that it should be legalized. So the confidence interval is a little tricky in that respect, right? Because it depends on the particular sample that you get. But you're safe to say, always safe to say, with 95% confidence or with 90% confidence, whatever level of confidence you want to use. All right. So we're going to skip the other examples, and I want to show you the traditional way of constructing a confidence interval, which you are not responsible for, but I want to show it to you anyway, so that you understand how people typically construct it, and not Stackey, but other people construct it. And here's the formula that's used. Now, if you remember from chapter 19, there was a rule for sample proportions that they mentioned in there, rule for sample proportions, that said something about the standard deviation of the frequency curve for all the various sample proportions that we could possibly imagine. And we would come up with this formula of the true proportion times 1 minus the true proportion, it says here, divided by the sample size, taking the square root of the whole thing. All right, so we're taking the square root of that whole thing. Now, again, we're not going to be using this when we create our confidence intervals, but this is the traditional way of doing it. And what we do, and this is, by the way, called the standard error, which, again, you're not responsible for that because they do mention it here. And they also say something like, if we want to create a 95% confidence interval, the margin of error is calculated by taking the standard error, which is that square root formula, and multiplying it by approximately 2. And then 2 times that standard error is our margin of error. You don't need to know that for doing in this course, but I'm showing it to you because that is the way, if you were taking a real stack course, that's what you would be using. Now, instead of using 2, you'd use 1.96. I'm not going to get into why. That has something to do with the empirical rule, but we're not going to get into that. All right. So that is the formula that's used to create our margin of error, and we add and subtract it from the sample proportion that we get in our sample that we have, and we got our confidence interval. All right. And let me see if there's anything else here. Again, they have examples and they show you how to calculate all of this. That's why we're not going to cover it in this course, because if we were, then you might as well do it this way. But and they try to make it easy by saying, oh, well, the standard error has to be multiplied by what's called a multiplier. Here are the multipliers that are used for confidence levels and so forth. But we're not going to do that. All right. And then they talk about how it's derived, and we're not going to do any of that either. And at the end of the chapter, they have formulas, right? You have formulas at the end of each chapter, and then here's the, again, it looks complicated, doesn't it? This is this formula for our confidence. All right. So let's forget about this for a second. We're going to get ourselves out of here, and we're going to go to Stackey. All right, so just give me a second and highlight Stackey. All right, so here is Stackey. Yeah. So instead of using those formulas, and that's why I showed it to you, because I want to have you compare what we're doing, comparing to what I just showed you. Instead of using those formulas to create confidence intervals, we're going to use this thing called a bootstrap confidence interval, which was described a little bit last time in that second video. All right. So in this chapter, we're dealing with single proportions, confidence interval for single proportions. So let's see how this works in StatCube. All right. Now, what we're going to do is in this particular section here, we're going to create our own survey. And if I hit edit data here, let me just go back. There's a button up here called edit data. And what it's going to do is going to give you a screen where there's two entries that you can enter. Number one, the second one here is your sample size. Suppose we want a sample size of 80. We want 80 people that we're going to survey. So we'll put 80 in here. All right. And suppose we want to create a proportion, a sample proportion. Let me think of an example here. Hold on one second. See if this works. My calculator. That doesn't work. All right, let's use a sample proportion of 0.25. A quarter of that sample is 20, right? A quarter of it's 20. So if we type in 20, 20 divided by 80 is 0.25. It's 1/4. It's 1/4 of the sample we're saying is answering a question a certain way, whatever that way might be. All right, so that is our sample proportion. We're going to just click OK. And notice over here, it tells us our original sample has 80 people in it, and 20 of them are answering yes to a certain question. And that's a quarter of that 80 people. That's 20 divided by 80 is 0.25. So that's our sample proportion. And suppose we want to generate what's called a bootstrap sample. What is a bootstrap sample? It's going to take the same 80 people, and we're going to choose people at random, all right? People at random from that sample, all right? And we're choosing them with what's called sampling with replacement. That means once we choose somebody, we can put them back into the sample, and then we can possibly choose them again. All right. So in this way, it's possible that when we choose another sample of 80, all right, there might be some repeats. Some of those people might be chosen more than once, and some people may not be chosen at all. So this creates some variation, different types of samples with different proportions. So let's just choose one of them. And notice in this particular case, we came up with a sample where 23 people instead of 20 people. The original sample says 20 out of 80 answered a question a certain way. And the bootstrap sample, this is again using a random number generator, just saying, all right, we'll just choose people from the sample of 80, and sometimes we'll repeat the same person. It's possible. In this case, we can come up with a count of 23, which means there were some people that we counted more than once. Okay, that's possible. In this case, obviously, it's not only possible, it happened, right? Because 23 people showed up in this sample, and 23 divided by 80 is 0.288. That's our sample proportion. That's called a bootstrap sample. So it's a variation of the original sample. And let's generate another one. And this time, 21 out of 80 were chosen, again, randomly, which is proportion 0.263. So we continue generating these. All right. You can see different numbers are showing up as the bootstrap sample. All right, and we've now chosen 11 of these people. And let's choose another 100 of them. And now we're seeing a dot plot being created here with all these various possible values. All right. For example, for a proportion of 0.3, we have 1, 2, 3, 4, 5, 6, 7 people that were 7 samples. Not 7, yeah, 7 bootstrap samples that had a 0.3 proportion, just like the one we just, not like the one we just did, but there are 7 of them, 7 out of the 111 that have 0.3. These over here, there are 3 that have a proportion 0.3313. All right, get the idea? So there's repeats over, and so we're creating this dot plot. And if we create another 1,000 of these samples, it starts looking like a bell-shaped curve. Okay, so we come up with this distribution here. There's 1,111 of these possible samples. And how big are each sample? Size 80. There's 80 people in each one of these 1,111 samples. So picture 1,111 people sampling this from the same population, sampling 80 people from the same population and asking the same questions, right? And each one of them get a different number of possible counts of people who answered the question a certain way, right? Now, what if we wanted to find a so-called confidence interval from this? What we do is we go inside this box here and click two tails. So we click that. Now this program automatically gives you a 95% confidence interval. Automatically does that by default. Okay. And how do we know? Because it gives us the numbers right here. This is the lower end of the confidence interval, and this is the upper end of the confidence interval. So this 95% confidence interval goes from 0.163 on the low end to 0.35 on the upper end. Now, how does the computer know this? It's because all the black dots, now you can't see all the dots, but if I run my cursor down, you can see these are dots here. All the black dots here represent all of the intervals that contain the true population proportion, and the red ones don't. The red ones are outside of the interval. All right. So what we're saying basically is, using simulation, that we're 95% confident that the true population mean is somewhere between 0.163 and 0.35. So this is an alternate way of coming up with a confidence interval using the original sample that you got, the 20 people out of 80 that answered the question a certain way. That's our sample proportion. And we end up with this interval, this 95% confidence interval, without having to use a formula, without adding and subtracting a margin of error. No formulas. Now, if I repeated this process, by the way, and if you just remember these numbers, 0.163 and 0.35, if I reset the plot, I can reset, I can start all over again, by the way. Reset it. And I'm going to do 1,011 again. I'll do 1,000, right? 111. And click the two tail button. And I'm going to get with, now what were the numbers before? Was it 0.163 and 0.35? Was it exactly that? Or is it something different? Anybody? Was that the same numbers?
Yeah, that was it.
Yeah, but it doesn't have to be the same numbers. It could be there could be some variation there, by the way. Could be some variation. But you should get, and if you repeat the process, you should get an interval that's close. This, by the way, this plot here is not the same as what we got before. So it is possible to get a different answer here for the 95% confidence interval. And that's because it's a simulation. The computer's generating this randomly, all these samples. How many samples are in the sampling distribution? Millions, zillions of them. We're only choosing 1,111 of these possible samples. So even the plot that we're coming up with here is going to be different. Each and every time we do this, and from all of you, each one of you will come up with a different looking plot. But the important thing to notice here is it does give us a confidence interval where we can make a statement such as, we're 95% confident that this particular interval will contain the true population parameter of 0.25. All right. Now and I should clarify, 0.25 is not the population parameter. It should, we don't know what it is. What's 0.25? It's the sample proportion for the sample that we chose. All right, that's the 0.25. We don't know what the population proportion is. We're just hoping, 95% confident that that population proportion is in between these two numbers here. Okay? And how does the computer come up with these numbers? It basically, if we want 95% here in the middle, that means 95% of the 1,111 samples, 95% of them will be these black dots, and 5% of them will be these red dots. 2.5% on the left, 2.5% on the right. All right, so that's how the computer figures it out. It's not that hard to figure out. So the answer is going to be these two numbers for this particular running of the stat plot. Now, what if I said something like, I want to change the level of confidence from 95% to 90%. All right, so how do I do that? And what do I mean by 95%, 90% confident? What I'm doing basically is saying, all right, I can be less confident. I'm okay with 10% of the possible samples being not containing the true population proportion, and 90% do contain it. I'm okay with that. I'm willing to go with that. Now, let's type in, what we do to get to 90% is you just go into this blue cell here with has the 0.95 and click it. And you can put in another proportion. I want to put in 0.9. Now, I have to tell you, when they say proportion here, they're referring to the confidence level. And that's another thing I would explain to the StatKey people here. They should have said, enter another confidence level in here instead of proportion, because it's confusing because we're dealing with proportions here. It's a bad word to use. But I'm going to put 0.9 for 90%. So this now represents a 90% confidence interval. And the numbers that we come up with now, notice the one on the left remains 0.163, but the one on the right is 0.325 now. That means the interval is naturally more narrow than it was before. Okay? Now, the only thing we did was change the confidence level. It's the same group of 1,111 samples. That didn't change. We just changed the confidence level, and we're getting a narrower confidence interval. This interval is 0.163 to 0.325. The previous one that we got was 0.163 to 0.35. It was wider. Now, that is, and you need to write this down, because it's not clear in the book, so write this down. When we lower the level of confidence, we make the interval more narrow. When we lower the level of confidence, we make the confidence interval more narrow. Now, is that a good thing? The answer is yes. It's a good thing to make the interval more narrow. The more narrow you make the interval, the better chance, no, I shouldn't say better chance, but it means that the variability is less. We want less variability, all right? We want the values of all these samples, the sample proportions, to be close to one another. That's always better than for them to be farther apart. We want less variability, not more. So that's a good thing. We always strive for that. However, the bad thing is, if we want to call it a bad thing, is that we lowered the level of confidence. We have less confidence now that this particular interval will contain the true population parameter. Because now only 90% of the intervals contain the parameter and 10% don't. Now, let's go back in here and change this to 0.99. Now we're going to increase from 0.95 to 0.99. Hit enter. And notice in this case, we're 99% confident. That's a good thing, right? We want to be more confident. That means 99% of the intervals contain the true population proportion and only 1% don't. But look what happens to the interval. The interval becomes wider. Hold on. Interval becomes wider. It goes from 0.138, which is less than 0.163, and it goes all the way up to 0.375, which is bigger than 0.35. So here's the other statement. The bigger the level of confidence, the wider is the confidence interval. The bigger the level of confidence, the wider the level of the confidence interval. Now remember, you don't want wide confidence intervals. So this is what's called a trade-off. You've probably heard the term trade-off before. We're increasing the level of confidence, but the trade-off is we end up with a wider confidence interval, which means there's more variability between each of these samples. That's not a good thing. When we lower the level of confidence, which is not as good as a 95 or 99% level of confidence, when we lower it to 90%, we end up with a more narrow confidence interval, which is a good thing. So there's a trade-off. If you increase one, the other one goes down, like that. You see what I'm saying? So how do you get around this? How do people get around this? And there is one thing that you can do. And let's go back. And this is where looking at the formulas does help, just for this one purpose. So I'm going to go back to the book. Give me a second here just to get squared up. Here's the book again. All right. I want you to take a look at this formula right here. This is the formula for the margin of error that they talked about on the book. And this small n here represents the sample size. Now, if we want a narrow confidence interval, all right, we either want Z here, which is the level of confidence, by the way. That's what it means, level of confidence, Z here. We either want that small, all right, because then we're adding, subtracting a smaller number here, or we want a big N. Big N, N is the sample size. If the denominator of a fraction, this is a fraction here, if the denominator of a fraction gets bigger, I hope you understand that the whole fraction gets smaller, right? Think of the fraction 1/2. If I change the denominator from 2 to 4, I now have 1/4, which is a smaller number than 1/2. So when you increase the denominator, the fraction gets smaller. So another way of making the interval smaller or less wide or narrower, however way you want to say it, is by increasing the sample size. So if you want the best of both worlds, you would, if you wanted to, let's say you wanted to make this 95% confident, right? But you wanted a more narrow interval, you would increase the sample size to make the interval more narrow. Increase the sample size will also do that. So you can write that down. Increasing the sample size makes the interval more narrow. Decreasing the sample size makes the interval wider, which is not what we want to do. It's always preferable to have a bigger sample size. Now you may ask, why don't people always make big sample sizes? And the answer is because it costs money, it's a lot of time and effort, and so sometimes you just can't afford it, you don't have the time, all those sorts of things. So you may be limited in the ability to increase the sample size. But if you can, it had an unlimited budget, you had an unlimited time, then that's always preferable, increase the sample size. All right, so I wanted to show that to you with this formula so that you could see mathematically, right, numerically, why that's true. Because the smaller the margin of error, and that's the other thing that you can write this down too, the smaller the margin of error, the more narrow is the confidence interval. The smaller the margin of error. All right. Okay, any questions about that? All right.
The smaller the margin of error, what was the second part of that?
Okay, the smaller the margin of error, the more narrow is the confidence interval. And it was the smaller this number is, this whole number, whatever this number ends up being, the smaller, the more narrow the interval is going to be. Okay?
All right, thank you.
Okay, no problem. But this is the traditional way of creating the confidence interval. You take your sample proportion and you add and subtract this number, which is the multiplication of this z times this standard error. That's the traditional way of doing it. Again, in this course, you're not responsible for this, but again, I'm showing it to you just for the reason so that intuitively you understand how to change the conditions of your research study to make the interval more narrow and maintain a certain level of confidence. And it's by increasing the sample size. That's the way to get around that. Okay, so let's now go back to StatKey just for a second. Just give me a second here. All right, so you get the idea that StatKey does give you a way without formulas to create confidence intervals that are very similar, by the way. If we, I'm not going to show this to you, but if you use those formulas, given the information that you're given in this example, you would come up with an answer very close to the interval that you're seeing. Okay. Now, what do these numbers represent here? These numbers here represent 1/2 of the difference between 1 and the confidence level. So 1 minus 0.99 is 0.01. Half of that is 0.005. Half of it's 0.005 on the left. And the red dots represent 0.005. All the ones that are on the left here represent 0.005 times 1111 samples. So that's the number of samples that are in red here. And the same thing on the right. That gives you the same number of samples on the right. All right. So that's what these numbers mean. You add these three numbers together, you get 1, which means 100%. All right. And it's the same thing if you change the middle number to 0.95. Then what's left after 0.95? 1 minus 0.95 is 0.05. Half of it is 0.025. Half of it is 0.025, right? You get the idea? So these three numbers add up to 1. And then 0.025 times 1111 are the number of red dots on the right. Same thing on the left. Okay, that's how they determined all of this. Now, what if we wanted to create a confidence interval for a mean instead of a proportion? So what we're going to do now is we're going to go out, and we can always go back to the main screen by hitting the StatKey button. And we're interested in finding the confidence interval for a single mean. I'm going to click that. Now, it defaults to mean here. It says bootstrap dot plot of a mean, but if you want to, if a person wanted to do a median or standard deviation, you could, but we're only going to do mean. So just leave it as a mean here. And to do this particular samples, we have to choose, we actually in this case have to choose one of the data sets that are given in StatKey, or we can upload a file. Now, there is in the StatKey information. There's information about how to do this. Upload a file. I believe you can upload it actually tells you here a CSV file, which is similar to a Excel file, CSV, or a text file. You can do a text file. So it tells you how to do it. Obviously, I'm not going to have you do it, but I may actually create one and put it into StatKey for you to use. Maybe during a test or something, I may ask you to actually create something with that file. So I would actually upload it for you to use. But let's just use one of the ones that are in here. And the one I'm going to use is, let me see, look at Manhattan Apartments here. There's only 20 of those. I went one with a nice sample size. Here, Florida Lakes, Mercury, and Fish. Here we go. So here's a sample size of 53 in this sample. All right. It's measuring the amount of mercury in fish. All right. So I guess they sampled in the lakes, some lake somewhere in Florida. They sampled 53 fish, determined how much mercury was in the fish. All right. So the mean is 0.527. It's in some sort of, I guess, in some sort of measurement, maybe millimeters or something. I'm not really sure how you measure mercury, but that's the mean of the 53 values. And the 53 values are shown in this dot plot, all right? So it runs as low as 0.04 amount of mercury in a fish all the way up to 1.33 amount of mercury, all right? So each of these dots represents one of the fish, one of the 53 fish. So we're going to do the same thing as we did in proportions. We're going to sample from these 53 fish. We're going to sample with replacement, which means we could reuse that same fish again. All right. It's possible that there might be repetitions of these values, and some fish will not show up on a bootstrap sample. So I'm going to create one of these samples here. All right. So in this case, here are the 53 that were chosen. Notice that the very last one, which is 1.33, is not chosen for this sample. And the only one that was chosen, the biggest one that's chosen is 1.2. So here's the 1.2, and it looks like the 1.16 and the 1.23 were not chosen either for this sample. Right? So this is the one bootstrap sample. The mean of that one is 0.484. They do give you a standard deviation, obviously, for each one of these. And they plot it over here. Here's that one bootstrap sample. So if we choose another one, the second one has a mean of 0.505. All right. So there's the 1.2 shows up. The 1.33 shows up in the sample, but the ones in the middle, the 1.23, 1.2 do not show up in this sample. And you can see there are some of these here that show up more often or repeated from the original sample. All right, so that's plotted. Where's that plotted? It's plotted right over here. That's that one. And let's generate 10 more samples. All right, another 10 samples, another 100 samples, maybe 200 samples now. All right, so you can see actually the plot here of the distribution of these 220 samples starting to look like a normal bell-shaped curve, right? And let's choose 1,000 more, maybe 2,000 more. So now we have 2,222 samples that we've chosen. All right, these are all bootstrap samples, and if you run your cursor over any of these here, it will show up over here as the mean and everything for that particular sample. So the one I've chosen here has a mean of 0.556. All right. So once again, I'm going to hit the two tails here. And again, what's the default will be a 95% interval. That's the default. And that interval will run from 0.437 all the way up to 0.615. All right, that's our 95% confidence interval from a bootstrap sampling. All right, so all these samples, all 2,222 samples, all of them are bootstrap samples of the original sample. And they all vary, right? They all vary like this, like a bell-shaped curve, just like we would hope. And if we did a 95% confidence interval, what we're saying is we're 95% confident that this sample, our sample that we got, that one sample, right? We're 95% confident that the true population mean, which is unknown, is somewhere in between these two values, 0.437 and 0.615. Now, if I ran this again with 2,222 samples, all right, so 2,222, and did a two-tailed test, we would get something a little different for our confidence interval. Right? It may not be exactly the same numbers as before. It would probably be close, but it may not be exactly the same. It was actually the distribution here would be different, but these two numbers could vary a little bit. All right. So that is how you do it when we're measuring a mean. We're measuring something, like in this case, the amount of mercury in a fish. Again, if we wanted to change the level of confidence, so in this case, that amount of mercury runs from 0.43 to 0.624. And if we lower the level of confidence, do you expect the interval to be more narrow or less narrow? If I lower this to 90% level of confidence, do you expect this interval to be more narrow or less narrow?
Narrow, more narrow.
More narrow, right. So let's see if that's true. We're going to change this to 0.9. Make sure you write it as a decimal. And now we see it's 0.448 to 0.607. Definitely more narrow, right? Definitely more narrow. The distance between 0.448 to 0.607, we subtract those two numbers, it's smaller than the original numbers that we got, which was, again, let's go back and type in 0.95 again. All right, this distance is wider, isn't it? Now, what happens when we change this to 0.99? Do we expect it to get more narrow or less narrow?
Less.
Less narrow, right. Or wider, right? That's it's a funny way of saying less narrow. Or wider. We would just say wider, right? It's wider, isn't it? This interval runs from 0.41 to 0.654. This is actually a pretty good example, right? Where you can clearly see how the intervals change based on the level of confidence. All right. So let me tell you, you guys have an advantage here since your tests are going to be open book. You'll have StatKey available. You could have it opened up during the test, and if you're not sure, if you're not sure which way the intervals will go, whether it'll become narrower or wider based on the level of confidence, you can just go in here and play with it, right? Just pick a data set and change the level of confidence in the middle here and see what happens. All right, and that's exactly what I want you to learn from doing this is this idea of how the interpretation changes. So in this case here, we would say with 99% confidence, that means 99% of the intervals should contain the population parameter, and only 1% will not. So we're 99% confident that the interval that we do have, or the sample that we do have, right, has an interval that contains the population parameter. Because we don't know what it is. We don't know what the true mean is, but we're 99% confident it's between 0.41 and 0.654. Okay? And that's pretty easy. I think confidence intervals are easy for students to understand because it makes sense, right? It makes sense what we're doing here. It's just the interpretation. You have to make sure that you do not fall into the trap saying the probability that the true mean is between these two numbers is 95%. You can't say that. That's incorrect. All right. And that's because we can choose other samples. We could have chosen other samples, right? Other than the one up here, and we would get a different interval here. We get a different answer based on the original sample that we end up with. We end up with a different interval, and we can't say that there's a 95% chance that the true mean is between that interval either. No, that's not the interpretation. We have to say that of all the intervals, we're 95% confident the one that we chose, and the confidence interval that was created from that actually contains the population mean. All right, that is it for today. Any questions? All right, so what we're going to do next time on Monday is continue using StatKey and come up with how to do both do confidence intervals for the cases where we're comparing two subpopulations, and we're taking the difference in their means or the difference in their proportions, and we're coming up with confidence intervals for those differences. So it's a little more complicated, but not really. I think you'll understand it. But I wanted to do that on a separate day, so we'll do that on Monday. All right. And just as a reminder, next Wednesday, there will, just because it's a day before Thanksgiving, there's no virtual class that day. I will pre-record that session on an introduction to hypothesis testing. I will pre-record it, post it for you to watch at a convenient time, all right? Because I know some of you will be doing Thanksgiving with your family. All right, I'm going to stop the recording. Any questions? No questions? All right, see you on Monday. Have a good weekend.
Bye.
You
Thanks.
too.
Yeah, you too. Bye-bye.